Okay. Yeah, I'm resuming now the explanation of still the same slide by saying now we would like to study the Gabor frame operator via these new tools. So the first thing is recalling again that we're doing row multiplication. The G is our Gabor system, and when we are applying it to a row vector, we apply first by doing analysis. So we have seen either we're doing a short time Fourier transform at the points of our marked lattice, or we are building this family of vectors. We call it a Gabor frame, and we're taking scalar products. And then doing synthesis afterwards is, in this case, linear combinations of these row vectors, and that's exactly the Gabor frame operator. So this time I have called it SGAB, so S standard notation for frame operator. And to check whether this is a reasonable good operator, I was checking the condition number, and that's fine. Next is I would like to tell you or give you an indication about the role of the adjoint lattice. Maybe I already put it here. The lattice that we are using is the lattice with the lattice points A and B, and the adjoint lattice, which will play a significant role, is the lattice in this case with n over b, n over a, or we could say I will call it A0, B0 now. But the first thing is that I'm verifying an interesting property of the Gabor frame operator. So the Gabor frame operator is, maybe I would say, well, first maybe I'm demonstrating that it is commuting with all the time frequency shift operators which correspond to the lattice that we have. So maybe I can do here I'm showing you our lattice. And maybe with sorry, I have to do a short break. So I'm just showing you that we have these lattices, and clearly you have a trivial way to describe the lattice by the two generators. You're shifting by multiples of A, 0, A2, A3, A, minus A, and so on, and multiples in the modulation direction. So if you want to know whether the time frequency shift the frame operator, the supposed Gabor frame operator, our SAB, is commuting with all these operators, it's enough to see that is commuting with the time frequency shift operators. Okay, so let me see. Yeah, so the matrices. I see, I think I have to do a new share. Sorry for this. No. Yeah, I think now I think it's correct. Maybe it was correct anyway, yeah. But yeah. So I'm creating TFM1 is the time shift in the A direction. TFM2 is frequency shift, and then I'm verifying first of all that my other command, which efficiently builds the matrix without matrix multiplication, which is the call Gab frame matrix. So give me the Gabor frame matrix with window G and time shift A and frequency shift B, or the one which we got by multiplication. You see it's not exactly the same, but numerically it's the same. And then I'm testing whether it commutes with time shift and with frequency shift, and you see this is true. Now the next thing is I would like to see what can we say about the spreading domain or spreading representation of this operator. And to look at the individual values would not help a lot, but when we look at this thing, maybe I'm doing also plot arcs here, we see it has a certain pattern. And the point at the end will be to recognize that matrices which commute with time frequency shift operators from the lattice are exactly those who are having a spreading function sitting on the orthogonal lattice. So again, we have the question, where do you have non-zero or significant values of this operator? So once more, SPRS is the spreading representation of our frame operator S. So we are getting it from the Gabor frame matrix. And we are looking at this. We see that they seem to be concentrated on some lattice. And now we can see another thing. Yeah, another thing would be, we could, that is a little bit distorted command, we could do a Gabor frame matrix from a random window. So no engineer would use a random window, but to see the effects that we get from the construction. So kind of, what is the properties of the lattice and what is the properties of the window? And the answer is, well, a random window creating a random Gabor frame operator with parameters A and B viewed at the spreading domain has a clear concentration, and I'm doing the same trick. I'm not, if you do it with SPI only, then it will say where is it non-zero, and if it's 2 epsilon, which is the precision of the machine, it will still say, oh, it was computed value 0 and not a true value. So we really have to put this here. You can maybe see the end of the code. Yeah, I was being a little bit generous. I took 10,000 epsilon. Yeah, to get a nice picture. If you take, yeah, well, you can play around. You can take 100 epsilon just to see. Probably numerical precision might give you some other contributions here. Yeah, no, it's not even bad. Yeah. So there must be some lattice, and the question is, of course, where it is. And yeah, I have problems with my window, so now it's better, hopefully. Okay, yeah, I see. So the problem is that I have to show you now so this was the end of this demonstration, and I have to demonstrate it now. I will try to do a splice hole of llama. If it works, it should demonstrate that I'm now plotting the points of this adjoint lattice. Okay, but that's not. Yeah, okay. Well, it's instructive in the way that you don't see any red points anymore. Maybe I should do it. I think the color code can be anything. So you have to trust me at this point by saying, well, I was first plotting the, I mean, yeah, it's still one command, yeah. Maybe we can do this here with yellow stars. I'm not sure if this works. So no. I think I have to put it separately. That's because it's not standard MATLAB. No. Yeah, no. I will try to fix it, and when you share the, there's something. I have a problem with the bars here, and one more attempt. Ah, I see. That shouldn't be done here. That was the problem. First I have to check, and now the input has to be plotted, and then only after this, the spy command, this has to be done to the spy command. Yellow and star. Yeah, that's now finally working. So first I plot the entries of the non-zero I show you in yellow, non-zero entries of the spreading domain, of the spreading representation of a random window, which means every yellow point is something where this spreading function is non-zero or small, big, whatever. And then later on I plot by keeping these yellow background points, and I plot this adjoint lattice, which is coming from n over b, n over a. And this is just an experimental evidence that the spreading function of a lattice is concentrated, the spreading function of a Gabor frame operator related to a lattice is concentrated on the adjoint lattice. That's kind of what we can see here. Maybe I'm showing you also the command adjoint lattice, and but maybe this is better done. Yeah, maybe I do it here. So the adjoint lattice was for a long time just the lattice with the lattice constants 1 over b, 1 over a. So somehow you think, well, if I do sampling, it means I'm sampling at the compressed Dirac comp, for example. So a is a small a, and that means if I go to the Fourier transform, I'm periodizing my spectrum with 1 over a. So it's orthogonal lattice is the terminology. Now, if you have a and b, you're saying, oh, with a and b, there's 1 over a and 1 over b. That's the adjoint lattice. But you also switch the roles, which what we have seen is the transposition of in our matrix case or so. And now the question is, how do you get the orthogonal lattice? And in MATLAB, I would say take the Dirac comp as a 0-1 matrix, and then take the two-dimensional Fourier transform. Yeah, maybe we can do this here. We can take a claim that you get by taking the two-dimensional Fourier transform of our lattice points, we get the orthogonal lattice. And what is the orthogonal lattice in the discrete setting? Well, it's again a matrix of size n, but now with lattice constants n over a and n over b. So this is coming from the one-dimensional situation. Let's see if this is true. And the answer is yes, it's true, except for the normalizing factor 720. Well, if you think of an abstract definition of an orthogonal lattice, you would say, well, the orthogonal lattice is something on the frequency side. So there's this marking certain frequencies. Well, which frequencies belong to the orthogonal group? These are exactly the frequencies which are constant 1 on my given lattice. So why is it called orthogonal group or so? Well, think in the plane. Well, it's, I don't know if you see it in the other audience. Today I have this shirt which has stripes. These stripes are parallel waves. You can say, well, a plane wave is going in a certain direction with a certain frequency. Now, if you're saying I'm living now in R2, your group is R2, and you're saying my group is the x-axis. So then you can say, well, what are the plane waves which are constant 1 at the axis? And you would say, well, these which are perpendicular. So in the two-dimensional Fourier transform, it would be the complete y-axis. So if you have continuous subgroups, there is some concept of orthogonality. Of course, if you're on the real line itself and you're saying the integer group is your group, and of course with the standard normalization you describe frequencies by the 2 pi I, then the orthogonal group is the integers again. That makes the Poisson formula so nice and so on. If you're in 2D, set 2D, or in RD, the standard lattice set D, it has orthogonal lattice set D. And then of course you can ask, well, what happens if I rotate my plane, my x-axis, by 40 degrees in some direction? Of course, the orthogonal thing moves along. So if you do it now with the integers, you compress the lattice, then you have a decompressed lattice on the Fourier transform side. If you rotate the lattice or you shear it, you just have to see whether this goes covariant or contravariant. Now, the thing that I wanted to mention, why is this 720 coming up? Well, our lattice has 720 Diracs. So the group has 720 elements. The trivial character constant 1 everywhere is of course true for every group. So it has picks up 720 Dirac values of 1, so it must be 720. Another observation is any other character in the orthogonal group also picks up 1s at those places by definition. And the interesting thing is, but you get 0 everywhere else, because everywhere else you have multiple additions of unit roots of order n, and the center of gravity of any sum of unit roots of order n is always 0. Or you can say the Fourier matrix is an orthogonal matrix. It has constant 1 in the first row and column. So all the others have to be perpendicular to constant 1, which means they have to sum up to 0. So that's why you can compute the orthogonal group by normalizing through the number of lattice points by the two-dimensional. And now the trick is to say if we take the same with the symplectic Fourier transform, and I have already computed the lambda, where we are taking the orthogonal but with the flip. So what kind of result do you expect now, actually? Think of a moment. What will be the outcome? It should be the same, but with some factor. And what is the factor?
Why isn't the factor 1?
Let's see. Yeah, okay. Yeah, okay. Now I would have guessed wrongly. Yeah. So there is some factor because the different normalization. So what is the factor 1.5 popping up so that you can read it as or think of it?
I don't know what A and B were.
Yeah, okay. So we are having an A, B, and the redundancy, then we'll see what it is. I'm doing my standard situation, yeah? So here it is, yeah. So we have 720 lattice points for the 480 dimensional space, which means that our redundancy is 3/2. Yeah, maybe it's interesting to say, to check now. We count the points of lambda. We know it's 720. We count the points of lambda, and we compute the maybe something like this, n divided by redundancy. Oh yeah. So of course this was nonsense. I don't want to have a sum over lattice points, but I want to sum over the full lattice. So I have to convert it, or I have to take the sum over the sum. So it's not supposed to be a column-wise addition. But also such things you learn something. Okay, you see, if you multiply with the or you divide by the redundancy. So in our case, 2/3 is a nice thing, and I don't want to try to do it now because playing around with the plots might be a little bit cumbersome or so. But one interesting thing which I found can be used also for further investigation is to see what is the intersection of the lattice with the adjoint lattice. So kind of the intersection in this case turns out to be something which is giving a nice redundancy. So I don't remember it anymore. Maybe I should show you. It's of course again a lattice which is relatively coarse, and you can of course then describe both the lattice and the adjoint lattice as multiple of this coarse lattice. I think, I'm not sure. Okay, better. So once more, the relationship between the number of lattice points, which is 720, divided by the number of points in the adjoint lattice, which is 320, is of course redundancy divided by 1 over redundancy, which is redundancy squared, which is 9 over 4. And I think I remember that if you take the intersection of these and you take 4 copies, you get the small guy, the 320 element, and if you take 9 copies, you get the big one. Yeah, okay, we could try at least this here. I mean, really do a plot lambda with red or so, and then pi hold lambda with blue, just to see if it works. Oh no. Yeah, there is a stupid typo here. I should both use with spine. Maybe I should even do a figure so that it's not. Yeah. You see, it's trying to plot into the old figure because hold is on. So the spy ch is spy in a centered way with the hold on, because I don't want to remove the old one. No. Yeah, of course, it's stupid. If I first plot the sparse lattice, I should first plot the dense lattice, and then so slowly we're approaching a reasonable way. Yeah. So maybe you don't see it so clearly. I do one last experiment. I think I can ask to use the symbol. Yeah, this is now much better. So, and maybe now, since it's working now, I just copy it, take a new section and do the same thing now with a joint lattice. So, yeah, what you see here in this second plot is that the adjoint lattice, which is now with green dots, you only need 4 copies of the blue lattice to get the green one. So we could also check the intersection of the 2 lattices must consist of 80 points then. 80 times 4 is 320. 80 times 9, which is visible in this position. You see here there are 2 lattice points in each direction until you reach the next blue one. So we're in a situation where we have at least 3 groups playing a role for the possible analysis or so. Now, maybe I show you, because we are getting towards the end of this section, I show you that it's not necessarily the same. It doesn't have to be a separable group, so with the lattice constants in the time and in the frequency, but we can choose other lattices. So I do the following. I take the lattice and apply the side digmat command to it. That was a kind of a side observation when we played around, and then we wanted to have more general groups or so. So, well, you have this periodic idea, and then you have to have subgroups. And then the question is, how do you create general subgroups? Meanwhile, we have a program that allows you to compute all the subgroups which have, for example, the given redundancy. So what are all the finite, a list, really a complete list of all the subgroups of set 480 times 480, which have 720 elements. If I remember correctly, it's 86 such subgroups. And it's funny, and the good thing is that if you just need some of them, so I take the lambda is slanted, is side digmat of our lattice lambda that we have here. And so I can show you how they compare. Now, the point is, side digmat turns out to be an automorphism of the group. So it's not just reshuffling elements, but it's an automorphism of the group. So if I start with a subgroup, I get a subgroup, and you see in such a situation, I would like to do a zoom on both the left and the right, and there is some funny, again, private command. This dual command is, I would like to zoom in a coherent way, and I look closer, both. So if you have several plots, it would say, oh, I know there are maybe 6 plots, go to the first, second, and apply the command which is following it. And you see, here you see it's kind of a slanting procedure, but still the description is the same number of points. And then I'm saying, well, we take the GABs, which is the Gabor basic family. Now it's not anymore so easy to generate this, but this is something you do at the beginning only. So I take the same Gaussian window, but I take this 0-1 set, which is the slanted gamma. I do this frame operator of this, which is we do coefficients and then synthesis. And then I would like to say the spreading function of this S GABs is mapped to spread of S GABs. And then we would like to see what we can do. What first of all, I'm running this. Oh yeah. And I want to see again whether they are also concentrated in some way. And yeah, I want to spy on this, where the absolute value of this spreading is larger than 100 epsilon. And you see it's again on a lattice. Now there is this expectation, which is a valid expectation, that this will be the adjoint lattice. So we have to find out, so the adjoint lattice in the standard literature is defined as the set of all the time frequency shift operators which commute with the original ones. So this is why it's popping up here. And actually this would be another experiment that I don't want to do today. You could create a random matrix, and then you conjugate it with, let's say, time shift from your lattice. And then you say, well, what is the effect on the spreading domain? And then you will see that certain spreading coefficients are multiplied with numbers which are not 1, and others are multiplied with just 1. And so you say, well, but the frame operator that is commuting with certain time frequency shift operators So its spreading domain must be concentrated at the places where it will be multiplied with 1 anyway. That's kind of the reason why this adjoint lattice is coming up. Now we don't have to, we are not able to follow these formulas now, but I would like to demonstrate you only that there is a joint lattice, which is lamb's adjoint, which is the adjoint lattice, which is computed by the way of the FFT of lambs. And I just want to show you that this is that this looks in the same way. So I'm showing you this lambda plot action graphic here, and then we are close to the end of today. Yeah. Now, if we look, there is a slant as if it was going down to the right, and this seems to be the correct one. And now, since we know that, or I've claimed that side-stigmat is an automorphism, from group theory, there is a plausibility argument that if we go now to this commutation relation or so, that probably we have to apply the same automorphism now on the adjoint group, or we have to apply to a kind of covariance. Yeah? So what I would like to compare at the final step now is, we could say, well, lambda, that's the adjoint group that you see here. And we know that llama was the adjoint group of the original rectangular lattice. So we can play around and say, well, maybe we should, and actually I don't remember, I really have to do it myself each time. We should apply the same command to the adjoint lattice. So the adjointness relationship is going, oops. Yeah, there is a possibility now that one of these things are not I think the error is coming from not because I'm doing the wrong thing, but because one of them, yeah, so the lambda is just a logical vector, not a numerical vector, and the comp norm is rather for comparing numerical vectors. Kind of, this is storage. For a huge matrix with 0 ones, you say it's just logical, you need 1 bit. Yeah, okay. And you see we're lucky. This is exactly the same. That means we could go on, and that's what I actually was doing for a while to get more lattices or so. We could say, no, if the trick works fine and I do a side-stigmat routine on my group, and now I can take the first one, for this, the one that we have already, this slanted one, and apply it once more and see kind of how many groups can I get by applying side-mat, side-mat, side-mat. And of course we know the side-to-mat must be the inverse. So you could also say, what was the side-to-mat doing? Well, it probably will slant in the opposite direction or so. And we can, I mean, this was for a while the state of the art, that we were creating all possible lattices, which are square lattices, with redundancy 3/2. So you can change the role of A and B, or you make A a little bit larger and B a little bit smaller. It's okay. And then you apply side-stigmat until you're getting the original one again. And then you make a list of all these lattices or so. And I would say, if I remember correctly, we got something like 90%. But it's an interesting question. If you go to higher dimension, there are now formulas for the number of lattices that you can have for a fixed number. I mean, for a fixed redundancy. So that's kind of the index in phase space can be given, and the number is huge. Just think about if we can have 86 lattices in the plane, and now you go to 2-dimensional signals, you have a 4-dimensional phase space, and you can say, well, you can take 86 in the space domain now, and 86 in the frequency domain. Or you're saying, no, I'm pairing the first time with the first frequency variable and do the same trick. And of course, these are just separable groups, so it's clear that there's a huge amount of lattices. And a good or interesting question is, what are good lattices? What are the good combinations of functions with lattices, so signals, windows that you should use or so? But I think for now we should, for today, my time is over, and I thank you for your attention.